In this video, we're going to take a look at the idea of forking a process. So to start off with, I just want to discuss a little bit of the idea of what this really looks like before we start looking at an implementation of fork and how that works inside of the actual C code. So when we have a program that's running, it's running inside of a process. Just draw this out here. So it runs inside of a process, which we'll just call the parent process in terms of our terminology here. Now, the parent process has a few different things associated with it. As we've discussed, it has a stack, it's got a heap, it's got some uninitialized data in the middle here, and then it's got like all of the program instructions associated with the actual program itself, and it's executing through those instructions. What we could do inside of those instructions is we can actually run what's called a fork. And what a fork will do is it will create essentially a copy of this process that will execute as well. So this process will also have a stack, it will also have a heap, and it's going to have a copy of the instructions of our parent program. So it's going to be a copy essentially for our purposes. So it's a copy of the parent process. It's got the same stack and heap memory, it's got the same instructions, and it's able to execute the code inside of the parent. And we call this a child process. Now, the reason why we might want to do this is because it can be helpful to split up work amongst multiple different processes. Those processes can work on whatever it's doing individually, and then at the end we can combine those results together to get an answer that lets us solve a problem potentially faster. So that's the main reason why we typically look at this kind of process. So understanding this idea, let's take a look at how we actually do a fork in C. What we're going to do is we're going to start off by running the fork function. And we would typically do that by setting a variable equal to the result of that. And that variable is going to be a PID, a process ID, as we would say. I'm going to call it child PID. I'm going to set it equal to the fork function. Now, one of two things is going to happen here. In the parent process, this fork returns the process ID of the child process. In the child process, this fork returns 0. And what's going to happen is the code is going to start executing for both processes from this line of code. So the next line of code will be executed by both the parent process and the child process. So if you're thinking about this, these lines of code will be executed twice, once by the parent, once by the child. Let me show you that. So if we go printf, I'm going to print out the value of that child PID. Okay? So we'll see what that actually is. So we'll do %d, I believe is the format for it. And we'll see if the compiler complains about that. We think that that's probably what it is. We'll print out that child PID value. Let's take a look at what happens when we do that. Do you see that one of the processes give us back 84371, which would be the process ID of the child. So this is the parent process. And the child process gives us back a result of 0. That's what the return value is for that child process. And notice that it did execute twice. So this line of code executes twice because after this fork, there's two processes that are executing from that point onward. So that's the general idea of fork. Now, one question you may have is, okay, we have both of these processes that are executing. How can I get the child process to do something different from the parent process? The answer would be that we could take advantage of what the fork function returns. Since it returns 0 to the child process, it's pretty easy for us to say, well, if the result was 0, then we're in the child process, so we could do some stuff with the child process. And if the result is not 0, then we must be in the parent process, so we could do some stuff for the parent process there. Easiest way to do this would be using something like a switch statement. So we could just switch on that child PID. And what we could say is we could say the following. We could say in the case where the value is -1, this would be our error case. So we could just do like a printf error forking process, something like that. And then we can break out. In the case of a 0, like I said, we're in the child process. So what I'm going to do is I'm going to just copy this print and I'm going to move it out here and say child process child PID. So you can see what the child process prints for this. And of course, we'll break after this so that it doesn't fall into the next condition. And then the default case, so any other case, which would be the parent process, we'll just go ahead and print out the parent process value. So generally what we're seeing here is that in both cases, we're going to be printing out the value, but this one we would consider to be the child process, since it would be a 0 for child PID. this would be the parent process since it's not 0. Let's go ahead and take a look at that result. As you can see here, the parent process child PID is 84433. And as I said, this would be the process ID of the child process. In the child process, this value is 0. So you can see that that is actually the case. In the child process, it returns back 0 from fork. In the parent process, it returns back the process ID of the child. So this gives you some basic intuition around the idea of how this is actually working. Now, there's a few other interesting things that we can discuss here. One of the interesting things is how these shared pieces of memory are handled in these processes. Because like I said, when we do this actual fork, we're creating essentially a copy of the data from the parent process to use in the child process. So what that really means is that if I were to do something like declare an integer up here and give it a value of, say, 5, I can access this value I inside of the child process. So let me show you that. So I could, set the value I, and I could show you that value here. And I could print it out of the parent process too. Both processes have the value because it was defined before the fork itself. When we get to the actual fork, which, noting that I should put this above the fork, when we actually get to the fork itself, what happens is we create a copy, right? So this I would be inside of our stack memory since it's inside of the main function. It'd be like a local variable. So that stack memory gets copied over to the child, and the child would also have that I equals 5 in it. And I can show you that here. When I run this code, we do see that both of them have the value of 5. Now, when I say that this is a copy, I really mean that it is a copy in the sense that if I were to change I in the child process, it would not change in the parent. So the parent and child are separate from each other in terms of memory. Although we create an initial copy, from that point on, if we change any values in either the parent or the child, it doesn't affect the other process. So let me show you what that looks like. When I run this code now, do you see that we get a value of 5 and 7? So you see that the child process gives us back a value of 5, the other one gives us back a value of 7. And actually, I should just write out these, right? So that way we can really make sure that we can distinguish between these child and parent. And that should make it a little bit more clear that we actually are getting that result, right? So you see the child I is 7 and the parent is 5. So you can see that that actually is the case, that we have a copy of that data. If I change it here, it changes only in the child process, not in the parent process itself. And this applies for all different types of memory. So not just integers that are declared up here. If I have things that are like static values, like up here, I can access them as well in the child. They'll be shared between them. Even if I have things like structs that require malloc, which would be placed on the heap instead of on the stack memory, we would also see those values placed in the child memory as well. So I can actually declare like a struct, which will declare up here. So let's say struct x new s. You can set that equal to a malloc of struct s, like this. And we'll generally see that we would have a copy of both of these available, right? So we'll see that sort of process here. So that's the malloc, size of, I want, like this. So generally we could see that, if I were to set the value of s to be, say, 6, I could access this pretty easily over here just by using sval like that. And you'll see generally that it will allow me to access and change that value. We could see here, it wasn't sval, it was new s, using the wrong variable name. So it's new s here, and that would be new s here as well. And generally you'll see that when I actually use the right code, we do get that result. So you can see here that the value is equal to 6, which was the value that was set all the way up here. So hopefully this helps to give you a nice little intuition around the idea of forking processes. We're going to take a look at multi-processing like this inside of applications because it's a very common thing that's done not only just in system programming, but in programming altogether. Multi-threading, multi-processing are very important concepts. So we'll dive more into these types of concepts, but this should give you a nice solid foundation of what fork really looks like and how it generally works. And I encourage you to try playing around with this a little bit more, see if you can really get things working, see if you can, understand how values are changing and how code is executing through these paths. We'll take a look at more examples as we continue on. So thanks so much for watching, and I'll see you in the next video.